2020, 2.3 million women were diagnosed with breast cancer. In 2020, there were 685,000 deaths globally due to breast cancer. And by the end of 2020, there were 7.8 million women alive that were diagnosed with breast cancer in the past 5 years. Made it the world's most
common cancer.
That's crazy. But you know what's even more crazy? Women are getting diagnosed later. So that means they're getting treatment in the later stages of their cancer. And as a result, there are very less chances of survival. Hi, my name is Prisha and I use machine learning to detect breast cancer. That way, treatment can be done much earlier and we can save so many lives. Machine learning is often thrown around like a buzzword. So to put it simple, it's the science of machines making decisions. Machines learn from data, they can draw patterns, and then make predictions. In this project, the machine is predicting whether the tumor is malignant, so cancerous, or benign, so non-cancerous. Something really cool about machine learning is that we can use predictive modeling and different types of algorithms to make predictions. The first thing I used is a decision tree classifier, which essentially classifies the data based on different parameters. As the name suggests, a decision tree, the tree essentially has two different parts to it: decision nodes and leaves. The leaves are essentially the final outcomes, so in our case it's malignant or benign. And the decision nodes is where the data is split. The second algorithm I used was a random forest algorithm. So this essentially gives me the output based on the decision of various decision trees. That's why it's, forest. Predicts by taking the mean or the average from various trees. So with that logic, the more trees you have, the more precise your output's gonna be. The third one I used was a logistic regression algorithm. Also help us with predicting the choice that's being made. It does this by the relationship between a dependent variable and one or more independent variables. It was so exciting that the random forest classifier had an accuracy of 96.5%. But how did I do this? There were 5 main steps I took in this process. The first one was importing the data. The second one was cleaning and exploring the data. The third one was data visualization. The fourth one was preparing the data before model training. Fifth one was training and evaluating the model. Alright, so now I'm gonna do a run through of the model that I made. Started off with importing my libraries. And then after that, this code basically allows me to import my file, which is data final.csv. So just go here and choose my file. And it's gonna print the first 7 rows of my data. Now I'm exploring the data and really just getting familiar with it. So I do this by counting the number of rows and columns in the data set. So I do this through df.shape. You can see that there are 569 rows of data. So there's 569 patients essentially that I'm getting the data from, and I have 33 input characteristics. Here I'm counting the number of empty values. So the reason why I'm doing that is empty values can often lead to miscalculation or just some sort of error in the output, which I don't want to run it. And I see they have no empty values except there's this column called unnamed 32. So that has 569 unnamed values. So I want to drop that, and to do that I run this and it drops all these empty values. And now to see the new count of rows and columns, I do this, and as you can see here, it's 32 instead of 33, which was here because one of the columns values has been dropped. I want to see how many malignant and benign cells are there. That 357 patients have benign tumors and 212 have malignant tumors. To visualize this, if you're more of a visual person, I can turn it into a graph through this ns.counterplot. As seen here, it turns those values from here turn into a graph. So now, the thing is, machines only understand numeric values. So if I use malignant and benign, M and B, as one of parts of my data, the machine is not going to understand that. So I want to see what kind of data types are numeric and what type of data types are non-numeric, and just what type of data I have. So that's why I run this, and through this I see most of them are numbers, except diagnosis is not a number because it is an object. Makes sense, right? Because it was M and B, malignant and benign. I need to change this because the machine's not going to understand what M and B is. So that's why I encode the data. So what this does is it encodes M to be represented as 1, so malignant as 1, and benign as 0, so B as 0. What I'm doing is a third step, which is data visualization. So part of that is I created a pair plot, which allows me to see the different correlation between variables and the category, which is malignant and benign. So now what I'm doing is I'm printing only the first 5 rows of data, and this is from the new data set that only had 32 columns. So now what I did was I got the correlation of each of the columns, and I saw which of the columns had an impact, which of the variables had an impact on each other. So essentially, as you can see here, diagnosis obviously had an impact on diagnosis since it's the same thing. The radius, positive impact on the diagnosis. The perimeter had a positive impact on the diagnosis. However, if I looked at, for example, fractional dimension mean, it had a negative impact on diagnosis. So these were a lot of numbers and very good data because I could actually see what each variable had an impact on what, but I needed to be more visual. So that's why I did this right here. And I created a heat map, which is essentially a more visual way of showing the correlation from here. So it shows essentially the same exact thing. For example, diagnosis 100%, so that's 1, except it shows it as a percent. Now what I did was I split the data set into independent and dependent data set. Put everything from index 2 to index 31 as X, and I put index 1 as Y. So if we just go back here, what I mean by index is this. So I did index 0 is ID, and then index 1 is diagnosis. So index 1, diagnosis, is Y, and then everything from index 2, which is radius mean, to 31 is index Y. And I split that data so I could work with it. And then what I did was I split the data into 75% training and 25% testing. This is really essential because if the machine draws patterns from some of the data, as an example, the training data, and you train that machine with those types of data, if you bring in a new data set, it might not be able to understand because it's just never been tested. So it's really important for a machine to be tested so you can actually, it can predict better. So now essentially what I'm doing is I'm feature scaling. And what this does, it ensures that all the features are within a certain range. And this is really important because it ensures that our output is, in a way, more realistic because all the features are in the same level of magnitude. Is that I'm creating a function for all the models, so logistic regression, decision tree classifier, and the random forest classifier, and then I'm printing the model's accuracy on the training data. And then when we run this, we see the accuracy of each of the models, and it's important to note that this is on training data. So obviously the accuracy is going to be higher because it's data that the model has seen, whereas if it's testing data, it's going to be data that the model hasn't seen, and therefore the accuracy can change. Logistic regression has an accuracy on training data of 99 if you round it 1%. The decision tree classifier has a training accuracy of 1, so 100%, and the random forest classifier has an accuracy of 99.5%, and that is all on training data. Now if we run this is testing the model's accuracy on testing data, which is important to note because this is data that the model hasn't seen before. So this is somewhat of a more true accuracy because it shows how the model will play out a little more realistically in the real world. Not completely accurate, but it's better than what we had above. And as we can see, model 0, which was our logistic tree, has an accuracy of 95.1%. That was model 0. Model 1 has an accuracy, so that's the decision tree classifier, and it has an accuracy of 93.7%. And model 2, which is the random forest classifier, has an accuracy of 96.5%. So as we can see, the random forest classifier has the highest accuracy. So we can also show this in another way, and that is through generating a classification report, which essentially measures the quality of the predictions made by the models. It shows us through a macro average, weighted average, and the accuracy we see here. So model 0, which was a logistic regression, 95.1, and so on and so forth. And it's important to note that you can make the accuracy of this model higher through more input data and testing and training the model and again and again and again. And that's obviously something that is important because you do not want to play with someone's life. Credits goes to this YouTube channel called Computer Science. Their video was super helpful. Recommend you check it out. I will link it in the description box. Well, that was it for this video, and I really hope you enjoyed it. If you did, please like, comment, share, subscribe, and hit me up on Twitter, hit me up on LinkedIn, hit me up on Medium, and I will see you back with another video very soon. Bye!